Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome you all in a RCC structure design. Okay, and in this lecture, basically, I am covering an example of one-way slab, continuous slab design, and the example is basically which I select from McGregor book. And this is the example you see. This is a grid system. Okay, you see here, and you see we have some secondary beams and then we have some girders. Okay, so these G3, G1, G2 and G4 are our girders, while these B1, B3, B5, these are our secondary beams. Okay, so what we have to do, basically we have to design this one-way slab system which is in between the beams and which is in between the beams. Okay, so you see this is the grid system which they define basically, and the exterior panel is 157-inch clear. Okay, this is the clear span, and this beam is 14-inch wide, but the parameter beam in this side, that is the north south direction, is 16-inch wide. So this beam is 16-inch and this beam is 16-inch, and here we have girders you see here. But as we see that this panel is basically 33 feet and 6 inch in length, and this panel is 15 feet 15 feet. So this is our basically our span length. Okay, this is a one-way slab system because 33.5 divided by 15 gives you a ratio more than 2, so that's why this is a one-way slab system. So what we have to do, we have to design this slab system. Okay, and we have this panel, all panels are same. Okay, and there we have some core. Okay, they may be used for different purposes. Okay, like a ventilator purpose, or you can say lift purpose. Okay, and this is all about the grid system. But before starting this example, I want to show you and I want to share you with some videos and some pictures that why I'm going to design this slab system. Because remember, the proper design of this slab system is very important. If you don't consider the requirements, the provisions of ACI code, so what will happen, then you will see in this video that you see that the beam is cracked at the middle portion. Similarly, the slab, this is an actual project which is basically what I have examined, and I see these cracks in this structure, and basically this structure is basically failed. You see the panels and you see the crack of the beam, and what I basically mean to share this video with you people, basically I mean that you must aware of the ACI provision, that if you don't fulfill the requirements of ACI code, so the failure is basically occurred. Okay, these are the requirements of ACI code basically that you have to fulfill. Okay, and this slab system is it is very important to note down that this slab the slab system which you see here is a two-way slab system, but this slab system is also failed. They will also crack. I will show you the cracks pattern of this slab system. But you see this beam, you see the crack which is the basically due to flexure of this beam, and let me show you the crack of that slab system. So here you see that in this pictures you see the cracks of the slab system. Okay, similarly here you see the crack of the slab system. So what basically happens in this slab system, because they don't provide the required thickness to the slab system. Okay, it basically needs 7.5 inch thickness from the ACI provision which I calculated, but they provide actually on the side that is 6 inches, okay, roundabout. So 1.5 inch basically they provide lesser amount of thickness to the slab system. That's why the slab system is cracked. Although the steel amount is perfect, you see the steel amount, and all other provisions are basically they are provided, okay, in steel. I mean that the steel is fully, you can say, according to the requirements of ACI code, but they are not maintain the thickness, okay. So deflection criteria is not satisfied and the slab system is cracked. So this is very important that you have to maintain, you have to provide the ACI code criteria, okay. Now coming back to the question, this is the question, okay, you see here, and this is the statement, and this is the grid system, okay. This is 97 feet, and in this direction it is 120 feet, and here we have the actual diagram, okay. This is the actual diagram. We have to design this one-way slab system here, this one, okay. This one basically, let me show you what we have to design. We have to design this slab system, okay, and this slab system. So what we have basically, we have given this span length is 15 feet and this one is also 15 feet, okay. So we have to just find out the clear span, okay, in this direction, and then we have to start our design. Clear? So the question is simple. I already shared so many one-way slab design slab system, and you see a strip of 1 feet is taken here, and you see the cross section right here, that here we have a beam, here we have 14 inch, and the edge beam is 16 inch, and the center to center distance is 15 feet. Clear? This is a secondary beam, okay, you see here, and this is the actual basically view of that slab system. Clear? So let's start the design. First of all, what we have to calculate the thickness of the floor system. It is very important. I already shared and I already explained in this video that they provide the required amount of steel in this slab system, but the thickness is not maintained. Due to that, the slab system is cracked, okay, and now this project is completely demolished, okay. So this is very important that you have to provide the required amount of steel. So from the ACI table 9.5, this table is basically define you different conditions. I already shared so many videos on this table, so please go to my channel and search that video. Already it is available, which gives the minimum thickness, okay, for members not supporting partition likely to be damaged, okay. So you have to consider this table, but remember there will be no partition walls. If you are placing some kind of partition walls, some heavy partition walls, then this table values will not be used, okay. This is very important to understand. In consultation with the architect and owner, it has been decided that the partition will be movable metal partitions that view. This statement is very important. Whenever you are fixing this, the thickness of your slab system, it is very important that you must consult consent with your architect and with your owner, and then you need to fix the thickness. So for in bay, we have the limitation of ACI code, that is L by 24. From that we got 7.17, and for interior bay, this is from ACI table L by 28, because we have a continuous slab system. In that slab system we have end bay and we have interior bay. So let me show you here. You see, this is our end bay and this is our interior bay. So for this we have L by 24, and for this we have L by 28. We have to choose the maximum one, okay. So this one will be governed, that is 7.17. so that's why try a 7-inch slab system, and assuming that deflection in the exterior span, chapter 9 will be, inshallah we will discuss it in chapter 9, but leaving this at this moment, we are just fixing the slab system is 7 inches and using 3 by 4 inch clear cover, okay. So this is the procedure to determine the effective depth, that is hole depth minus clear cover minus dB by 2. Let's say we are using number 4 bar, so that's why we are using 0.5 divided by 2, and 3 by 4 inch clear cover, we got our effective depth is 6 inch. Before the thickness is finalized, it will be necessary to check whether it is adequate for movement and shear. Remember, it is very important that you have to check this thickness in shear and flexure. Okay, so you must remember that whenever you are taking your selecting your slab thickness from this table ACI table 9.5a, it will be sufficient for your shear and flexure. Okay, this should be remembered. The loads are calculated. We have a factored load, slab thickness divided by 12 times the density of concrete, and here we have used superimposed load 20 psf and the live load is 80 psf. Okay, and the combinations are these two combinations, 1.4 dead and 1.2 1.6 live load. So this combination 2 is basically governed, that is 258 psf. Okay, gives us this value. And here we basically assume that our steel is yielding, and that's why we are using phi value 0.9. okay, now check whether the slab thickness is adequate for the maximum movement or not. So for that purpose, remember, we are using moment coefficient method. Now if we are using moment coefficient method, the moment coefficient method some requirement, and I already explained in my so many videos. Please watch those videos. But here you see the live load is less than 3 times of dead load. Okay, and remember there are some criteria. Okay, there are some criteria that if, let's say for example, your this span, this is 15 and this is also 15, if it is differ from this one, but how much amount it is, it should be differ, I think so, that is 20%. It should not be more than 20% of the shorter span. These are the ACI criteria. Please check ACI code criteria for whenever you are using moment coefficient method. Okay, so these are their limitations. Clear? Now those limitations are fulfilled right here, so that's why they are using ACI code section 8.3.3. the moment at exterior face of the first interior support is this one. Remember, let me show you those ACI moment. Remember, this is basically this one is basically, this is very important. Okay, this is one is very important. This is our end panel, and this is our interior panel, our interior span and end span. This is our interior, this is our first, our exterior support, this is interior support, first exterior support. Okay, interior support, sorry, and these are interior support. Here you see the coefficients, you see movement for shear, and here movement and shear coefficients. Okay, so at first support you see -1/10. Okay, and at the first face, okay, and at the interior face you see -1/11, and the coefficient you see here, this Cm is for movement and Cv is for shear. Okay, this table is basically available, these figures are available in McGregor book, okay, also in Nelson book, so you can check those. Okay, the movement at the exterior face of the first interior support. Okay, this should be clear here. This is our first interior support, and at the exterior face of the first interior support you see this coefficient is -1/10. So that's why basically they're selecting -1/10 times WU ln square, where ln for computation of negative movement at interior support is the average of the clear span. Remember, this is very important, you must understand it, that here we see 157 is clear span for first interior panel and 166 inch for the interior. So for negative movement, the movement which we will consider at this beam or at the first interior beam, okay, we will consider the average of these two, 157 plus 166 divided by 2. But for this panel we consider only 157, while for the rest of the interior we will consider 166 inch. So this is important. Okay, so here we have average, that is 13.5 feet, and using this average span we calculate the movement from that coefficient, and we have 4.70 feet per feet. For the second interior support we have minus WU ln square divided by 11. So you see here minus 1 over 11. Okay, you see here this one, this is for exterior face, but this is for an interior face. So the purpose of this to basically to got the maximum movement. Okay, because negative movement is always greater than positive movement in the continuous beam system or slab system. So in that case we have ln average, that is 166 13.8. In this case you see we have a movement of 4.47. so this one is governor. Okay, this is the maximum movement. And to calculate the A is the trial and error procedure is used, although you can use a direct approach. I already explained the direct approach in so many videos, and there are different some other aids of ACI they can be used. So please watch those videos. You can know the procedure how you can use the direct procedure. The formula which I have already explained right here, let me show you that formula. This is the formula which is used in direct procedure by ACI, and all things, all materials are available here. We have a B, that is 12 inch, depth 6 inch, MU is calculated, FC prime is 4000 psi, and FY is 60,000 psi. Okay, let me show you that FY in this example is 60,000 and FC prime is 4000 psi. So in this procedure basically you see D minus A over 2 is what? It is a lever arm, and a lever arm is denoted by JD, and remember that lever arm JD can be used 0.95 times up T. This, it may be approximately we will fix this 0.92 to 0.95 times up T. So that's why this value is be replaced by the by 0.95 D, and D is 6 inch. So do the calculation by yourself. You got this 0.183 inch square per feet. Okay, now steel is calculated. Now what we have to do, we have to calculate A. Okay, as Fy divided by 0.85. Okay, why we calculating this A? To check the yielding of the steel, to check whether the section is tension control or compression control. So to check the section we calculate C, that is A divided by beta 1. Beta 1 is 0.85 and A is this much. So divide this, you got the value, and that value should be less than 3 by 8, that is 0.375. If this value is less than 3 by 8, so this means that the section is tension control section. Okay, and if it is more than this value 3 by 8, this means the section is not a tension control. What does it mean? If the section is tension control, you are allowed by the ACI code that you will use P value is equal to 0.9. If this value is more than this 3 by 8, you cannot use 0.9. Then you have to calculate the phi value, the actual phi value, and how to calculate that, because you are going into transition zone or a compression zone, and I already uploaded so many videos that how that if basically if you watch the design of double reinforced beam in my videos, you will know the procedure how to recalculate this value if this value is greater than 3 by 8. Now here all the things are satisfied. That's why ACI code allows us basically to use 0.9. So again we calculate the A is, that is 0.178 inch square per feet, and this is the provided reinforcement ratio rho. Okay, A is divided by BD, that is 0.00247. Clear? So rho value. Okay, and you already know that how we calculate a rho value. So this is simple. Okay, you must know that rho is equal to what? Rho is equal to A is divided by BD. Okay, this is the procedure. A is divided by BD, B is 12 and D is 6 inches, A is calculated, we will get, but this is row provided, remember, and you already know that row provided should be less than row max, okay, and it should be greater than row minimum, okay, it should be greater than, but already this check is basically used for tension control section, but already we checked the section that is under control because this condition is satisfied, so that's why we don't need to check that procedure. Now we calculate this steel reinforcement, and this is a very low reinforcement ratio. This is very a low reinforcement ratio if you because this is 0.00247. If you calculate basically the minimum tensile reinforcement ratio, that is rho minimum, from two equation, that is 200 divided by Fy or 3 into Fc prime under root divided by Fy, it comes out to be 0.0033. okay, so ACI code basically do not allow in this case to use this ratio. We have to use that 0.0033. okay, but although let's say we are using this one, this is a very low reinforcement ratio as in common in most slabs, so clearly the selected slab thickness is adequate for the design bending moments. Before selecting reinforcement, we quickly check. Although in slab design shear is almost basically covered. If you select your thickness from those coefficients, from these by using these coefficients or these equations, okay, but although you can check it, it is not a complex procedure, it is easy. You have to just calculate your VU, that is 15% more, okay. This 1.15 WLN divided by 2 is basically selected from this here, okay. Here you see the coefficient for shear is 1.0, but for here 1.15, so that's why 1.15 times WLN square divided by 2, okay. This is the maximum coefficient. So from that our shear is basically 1940 pound per 1 feet of wet slab. This is the AC criteria, okay. 2 lambda Fc prime BWD, and you know Fc prime is 4000, BW is 12 and D is 6, so that's why just plugging the value you got 9110, and multiplying this with 0.75 we got 6830, which is well above that VU value. So that's why 7-inch thickness is okay of the slab. Now the procedure is design of reinforcement. We have to provide reinforcement, and what we have for end bay, we have a clear span of 13.1, okay. 15 is total center to center. Convert this into inches. 16 inches for the exterior beam and 14 inches for the interior beam. So that's why we got 157 inch. This is the clear span of the end panel, and this is the clear span for the interior panel. I already explained this, okay, with you people, that you see here 157 inch and 166 inch. How it comes? You see 15 feet for the end bay. This is center to center length. So center minus this 16 and half of that 14. Similarly 166, 15 minus half of this 14 and half of this 14. You got the required value. Clear? Now for the calculation of design moment in interior support, ln is taken as the average of the two adjacent span. This is, remember, for the calculation of design moment in interior support, if you, let's say if we are calculating, let me show here that if we are calculating the moment right over at this support, we will use the average of 157 and 166. If we are calculating the moment in the positive region, we will use this 157. And if we are calculating the moment, positive moment right at the mid of this panel, we will use this 166. This is very important to understand, okay, because many students will confuse right here. Now you see this table, this is the whole calculation. Basically they summarize whole this procedure in this one table. ln is basically for external support, that is 13.1. Clear? This is 13.1 for the external support. Remember, this is my external support. Okay, so if let's say, because you must remember that here we have a girder. Okay, so the slab interior, in this case, let me show you. This is very important point to discuss with you people. Okay, this is very important. Remember, in this case we have a slab system, and here we have a girder. Okay, here we have a girder, then we have a beam. Now this girder is, the stiffness of this girder is more as compared to this slab system, so that why the girder play a fixed support right here. So that why here we have a negative moment. Okay, we have a positive, then we have a negative moment. This is very important, okay, to understand. So here we have to use the coefficient, and here we have a positive movement, here we have a negative, here we have a negative. So to calculate this movement, what we have to do, basically we have to coming back here and see the coefficient. You see -1/24. This is for the girder for the first exterior support, and the length will be used 157 13.1 inch, that is a clear. Similarly at the mat we will use the coefficient 114, and similarly at this face we will use -1/10, and here we will use -1/11, and then we have 1/16, and then the procedure will be repeated. Okay, so you don't need to be confused with these coefficients. Now external support 13.1, exterior mat span 13.1, a first interior support 13.5, which is the average. And then remember, this is 157, this is the average 157 plus 167 divided by 2, and this is again 166 inches. Okay, again, and so on. WU ln square, we already calculated WU ln, just you have to that WU which we calculated in first step, multiply with this 13.1, you got this one. That WU ln square with this one, you got this value. Similarly with this, you got this value, and so on. Now M coefficient is basically taken from this diagram. Okay, from this diagram, and here you see -1/24. So let me show you. -1/24, 1/14, -1/9, or 1/10, -1/11, and 1/16. So you see all those coefficients right here. Clear? Now MU is calculated. How they basically calculated MU? The procedure is already known. WU, this value is multiplied with this coefficient, you got this value. Clear? And the next A is required. So A is required. How it basically calculate? Remember, a very simple procedure right here. You see the maximum moment is this one, 4.70, and the steel ratio, or the steel which is already calculated, that is 0. We already calculated the maximum, that is 0.178. So we will calculate a scale factor right over here. 0.178 divided by 4.70. This is another technique. Okay, in ACI this is another technique. Basically you must learn this technique. Once you calculate the scale factor, what then you need, you have to just multiply that scale factor with this moment, you got this steel. That scale factor with this moment, you got this. Okay, so the rest of the values of AS will be calculated by multiplying that scale factor with these moments. The next is AS minimum. AS minimum is basically from where this value is taken. Okay, this is 0.0018. Remember, if I show you this value right here, you see 0.0018 BH, and you got 0.157. Because if we go to ACI code section 10.5.4, which refers to section 7. Let me show you this section. This is very important to understand that how they basically select these coefficients. okay, these 0.00, these are the spacing limitation. I will discuss this later, but here I want to show you that 0.00, okay, this 0.0018, okay. So where it is, this section, let me show you this section. ACI section 7.12, okay, 7.12, this one, okay. Here you see the coefficients, okay. When we are using grade 40 and 50, we will use 0.002. If we are using this, as in this case we are using grade 60 steel, so we have to pick this one, okay. And if you are using more grade steel, then we have to use these one. Remember, I will discuss this, okay, I will discuss this. So that why basically they are choosing this 0.151. This is minimum steel reinforcement. Remember, this is minimum steel reinforcement. So that's why our minimum steel reinforcement is this one. But the calculated value you write, see here, all the values except this one, okay, except this one will be, but this one is also more than this one, this is okay. This one is less than, so we will bound to use this value. Similarly, we will bound to use this one because this is greater than the minimum. Here we cannot use this one, we cannot use this one. We will use this minimum reinforcement, okay. So for this 0.151, we select this amount of steel, number 4, at the rate of 12 inch center to center, okay. So how they basically get this value, you just need to this is the spacing, okay. We already choose number 4 bar, and if we have a number 4 bar, the spacing can be calculated by the formula, that is a simple formula, okay. You can use spacing equals to area bar divided by A is, which is calculated, times 12, okay. So area bar is 0.2, area of steel 0.151 times 12, you got the answer. But at the maximum spacing, ACI code have a code in case of a slab system, there are some restrictions. Let me discuss those restrictions. Here you see, here they explain the limits of ACI 7.6.5. Clear? For one-way slab sections where there is a required area of flexure reinforcement as indicated in line 5, for all slab section, ACI code section 7.6.5 limits the spacing between that reinforcement to smaller 3 times of H or 18 inches. Our is calculated is should never be greater than 18 inches or 3 times of H, okay, whichever is smaller. For this case, the 18 inch is governed. Now the next spacing for a crack control, the ACI code 10.6.4. Now remember, there are two criteria. One criteria is ACI code 7.6.5, but at the same time the criteria is 10.6.4. we have to fulfill this criteria as well, okay. That criteria is equals to 15 times 40,000 watt by Fs minus 2.5 cc, but not greater than this one. So how we can calculate Fs? Fs is 2 by 3rd times of Fy, that is for 60, okay, 40,000 for 60 grade 60 steel, and cc is 3 by 4 inch, we already selected. So here you see 12 inches. In this case 12 inches governor. Now if your calculated value from that formula, which I write here, from that formula, if it is more than 12 inches, so we cannot use this value. We are bound to the ACI criteria or provisions. So we have to use 12 inches. Our S should never be greater than 12 inches. So let me show you, let's say for example, let me check it, that 0.2 divided by 0.151 comes out to be 1 point this, okay, times 12. So you see 15.89. This is the calculated value of spacing, but as this spacing is more than 12 inches, okay, although it is less than 18 inches, but ACI criteria says 10.5.4 that your spacing should never be more than 12 inches. So that's why we are bound to use 12 inches. Clear? And the result override the 18-inch maximum spacing from the previous step. Thus, maximum bar spacing is 12 inches, which was used in line 7 and 8. Okay, this is very important, and let me show you. This section is basically 10. This section is 10.6.4. I already discussed that you must aware of the code. Okay, you have to basically read the code criteria. Remember, this is very important, and you have to command that how to use a code. Okay, sections. So this is section 10.6. Clear? So 10.6, where it is? 10.6, this one. Now you see distribution of flexure reinforcement in two-way slab system. Flexure tension reinforcement shall be well distributed with a maximum flexure tension zone. The spacing of the reinforcement closest to the tension face shall not exceed that given by this one. Okay, this one, and but not greater than this one, where CC is the least, and remember Fs is 2/3 times of Fy. This is very important, and at the same time you have to check that criteria as well. Okay, that 3 times of H R provisions of 10.6.4 are not sufficient for structure subject to very aggressive exposure. So this is very important. Clear? This is very important that you have a knowledge that how to calculate maximum. You have to calculate your spacing from this formula. Then you have to check with 3 times of H R 18 inch. Okay, and then again you have to check it with those limitations, ACI limitations. This is very important. Okay, so spacing is already fixed, that is 12 inches. Now on the basis of 12 inches spacing, you have to recalculate your final AS. Now how to calculate your final AS? As spacing is fixed now, so it will increasing your steel ratio, that is 0.20. Now this is the providing reinforcement. Okay, how to calculate? Again, remember spacing is fixed right now. Now if spacing is, let's say we fix the spacing that is 12 inches, so our area of steel now, area bar, that is 0.2 divided by spacing, that is 12 times 12. Okay, so this is the procedure how to calculate basically your these values. Okay, so 0.2, 0.2. Okay, now select the top and bottom flexure steel, that is number 4 bars. Okay, this is already selected, and you see this is the diagram basically which they draw. The shrinkage reinforcement is the same reinforcement. This is also from ACI code 7.12.2.1. okay, and basically we will provide for shrinkage the minimum reinforcement, and the minimum reinforcement is 0.151, that is 0.00. okay, so for that purpose they are basically using the number 4 at the rate of 15 inch. For shrinkage reinforcement there are also some limitations of ACI code. I will explain. Okay, but here we have those limitations. Remember, for shrinkage reinforcement, this is the procedure of calculation 0.151, and this maximum spacing for the shrinkage reinforcement should be less than 5 times of H or 18 inches, whichever is current. So 18 inches. So basically they are fixing that the shrinkage reinforcement is provided 15 inch center to center. Okay, this will result A is 0.160 inch square. And you see this diagram, this is the final layout of the steel, and the cut-up distance, you can see the cut-up point is basically 3 feet 4 inches. This is 157 divided by 4. You got 3 feet and 4 inch, and this 4 feet 4 inches is basically by the average of these 166 157. Okay, 166 plus r, I think so, 13.5 divided by 3. This is L by 3 and this is L by 3. So you can also select these cutoff points from the appendix, you see, 5A 5C. Okay, this appendix is available in the end of this book. Okay, you can see, and I explained, this is my channel. Okay, there are almost 18 videos on these tables, how to use those adds to select these points, because although the panel spans are same, so that's why we are allowed to use L by 3 and L by 4, those coefficients. But if it is not the same, let's say this is 15 and this is 20 feet, then we are not able to use those L by 3 and L by 4. We have to calculate those theoretical cutoff points and okay, actual cutoff points. So this is the whole procedure till now. Now the next procedure is that we have to design the transverse top steel at girders. This is ACI code criteria. Another criteria you see in this diagram, basically, that here we have, you see, this is a girder, okay, and here we have a girder, okay. So the slab system in this zone, basically, here we have a beam in this direction, and these girders are basically, you see here, in the direction of the one-way slab system. So that's why there is a basically near this region there is a two-way slab system, two-way action, and due to that action we have to provide some extra bar right over in the top portion of this girder. So basically here they are explaining that point, that due to localized two-way action adjacent to the girders G1 G2, ACI code section 8.12. This code requires that top transverse reinforcement be designed for the slab to carry the factor floor load acting on the effective width of the overhang flange. So ACI section 8.12.1. So let me show you this section. This is very important section that you must fulfill this section. Okay, this is a T-beam procedure. Okay, here you have to calculate the cantilever portion of a T-beam, and that cantilever portion is basically very important. These are the coefficients which basically selected. Okay, we will choose WU ln by 24 and WU ln by 16, and as well other coefficients. Okay, and the next one is 8.6, I think so. Yes, let me check it. 8.12, clear? 8.12. Here we have a T-beam construction, and in the T-beam construction, remember that 8.12.5, this one, where primary flexure reinforcement in a slab that is considered as a T-beam flange excluding joist construction is parallel to the beam, reinforcement perpendicular to the beam shall be provided in the top of the slab in accordance with the following. This is important. Primary flexure reinforcement in a slab that is considered as a T-beam flange is parallel to the beam, reinforcement perpendicular to the beam, okay, perpendicular to the beam will be provided in the following. Transverse reinforcement shall be designed to carry the factor load, okay. For isolated beams, the full width of overhang flange shall be considered. For other T beams, only the effective overhang slab would need to be considered. And you already know that that overhang portion in the case of T-beam will be equals to here 8 times the slab thickness or 1/2 the clear distance to the next web. And Inshallah, in next my video I will explain this whole procedure, how to fix, okay, the overhang portion of the T-beam. But here in this case you see this 3.25 feet. This is the overhang portion. You already know this procedure if you are study a T-beam procedure. Okay, in a T-beam, let's say this is a T-beam. Okay, this is a T-beam. So here we have a portion which is cantilevered. So this cantilever portion can be let's say this is the whole cantilever portion. There are ACI criteria. This B effective will be equals to the span length of this beam divided by 4R. This will be equals to 8 times of HF, I think so. And the next criteria is the here we have 1/2 the clear distance to the next wave, or the transverse. 1/2 mean that is the in this case basically let me show you. Here we have 33.6 in this case. So 33.6.5 divided by 2 R. This span, that is round about 13 something clear span, divided by, or 15 divided by 4 R, 8 times HF. Okay, so from by using those coefficients, okay, by these three criteria, remember, shall not exceed 1/4 of the span length. Span length in this case 33.5. That is 15 feet. R15. If you divide 15 divided by 4, you got that value, that is 3.5. 3.25, round about 3.27 feet. Okay, calling this, we will calculate WU ln square divided by 2. Remember, here we have a cantilever portion. Remember, here we have a cantilever portion, because in that girder, you see here in that girder, here we have a cantilever slab portion. Okay, and the maximum movement in this case right here, that is WU ln square divided by 2. Okay, this is the cantilever. Okay, you already know how to calculate the maximum movement in case of cantilever beam. So using this one, you got this value. So let's say we are using that number 4 bar at the rate of 12 inch center to center. We got what we basically got from this amount of steel. We got area of steel is 0.2. Now next, what we have, we need to calculate the effective depth. So the effective depth is simple, 6 minus 0.5, that is 5.5 inch. And because we have to provide, remember, we have to provide this amount of steel in the top portion. So in the top portion, basically the effective depth will be 5.5 inch. Now recalculating A. Why we are calculating A? So to find out this nominal moment capacity. So we have S, that is 0.2. 5 value is already decided. Fy we have, and we have, so this depth is basically, this effective depth is, remember, here we have, you must need to notice this sentence, that a smaller effective flexure depth will be used, because these bars, which is the transverse bars over the beams, over the girders, okay, will be used below the primary flexure reinforcement. So that why they are using the lesser amount of effective depth, and they calculate A, and then they plug the value, all the values, okay, in this equation. They calculate the nominal capacity, which is 4.82, and which is well above that value. So this ends up this procedure. Remember, this is very important step. This is very important step to understand this step. Okay, whenever you have this kind of slab system, you have to provide the steel reinforcement, extra steel reinforcement right over in this region, okay, in the top portion. and this is how the procedure is. Okay, and this is the final layout, the final design table. Okay, the whole calculation is summarized right over here, and this is the detailing. Okay, this is the detailing. Okay, this is the whole detailing procedure. If you want to become the master of detailing, you need to go to my channel, and in that channel you will understand, you will see these lectures. Okay, there are total 18 lectures which are uploaded. Okay, and these 18-inch lectures are basically relevant to detailing of RCC member, so you must watch those lectures, okay, to understand this detailing. And you see here this extra bars which is provided. Okay, and the effective depth is will be minimum, because here you see total 7 minus that clear cover minus that dia bar and minus this half the lower bar. Okay, and I think so the procedure is simple. I already uploaded so many videos which is just same to this example, so that why I'm not explaining all the things. Okay, and see you in next lecture, inshallah. In that lecture basically, which is the coming lecture, I will show the procedure how to design this beam system B3, B4 and B3. Okay, how we will design this Tbeam. So that lecture will be very fruitful for you people if you are watching the whole lectures of my channel. Okay, so thank you for watching. See you in next lecture.